Two galaxies are about to collide, and in their violent meeting, they will build something new. Galactic collisions are the hidden architects of our universe, a creative force shaping everything we see. By the end of this, you will understand the universe not as a static picture, but as a living, breathing structure under constant construction. We will uncover how these cosmic encounters weave a web of dark matter and decide the ultimate fate of our own Milky Way. What invisible blueprints are written in the chaos of colliding stars? How does a dance of destruction create the very framework of the cosmos? When you look up at the night sky, what do you believe is truly permanent? That early universe was a place of profound potential. Think of it not as empty space, but as a canvas still wet with the first brushstrokes of creation. A nearly uniform sea of dark matter and primordial gas was not perfectly smooth. Tiny, random ripples in density, smaller than you could possibly conceive, were the only things that broke the symmetry. These minute wrinkles held immense power, for gravity noticed them. Where there was just a little more mass, gravity pulled a little harder, drawing in wisps of gas and the mysterious dark matter. Over hundreds of millions of years, these gravitational anchors gathered more and more material, growing from specks into the glowing cradles of the first stars and the earliest, blobby proto-galaxies. This was the cosmic dawn, the moment the universe began to build its first neighborhoods. Without these initial clusters, there would have been nothing substantial enough to ever collide. So the stage was set. The universe had its raw materials and its fundamental force, gravity, ready to orchestrate a construction project of unimaginable scale. The simple act of falling together would now become the universe's primary creative tool. Our own galaxy is in a state of constant, breathtaking motion. The Milky Way is not simply drifting, it is being pulled, hurling through the void at a speed of over 600 kilometers every single second. Its destination is not a star or a black hole, but a vast and mysterious region of space known as the Great Attractor. This name evokes a powerful force, and it is, but not in the way you might think. It is not a single, monstrous entity. Instead, it is a gravitational focal point, a deep well in the fabric of the cosmos created by the combined mass of an immense collection of galaxies and the vast, invisible halos of dark matter they are embedded within. Why are we and everything in our local group of galaxies flowing so relentlessly toward this one point? The answer lies in the history of collisions and mergers that came before us. Over billions of years, these cosmic events have sculpted the distribution of mass across the universe, creating an uneven landscape of dense superclusters and empty voids. Our motion is like a leaf caught in a powerful river current, a current that was set in motion by the gravitational pull of this hidden architecture. This relentless journey is a silent testament to the invisible forces that guide us, a ghostly reminder that the empty space around us is not empty at all, but structured by the hand of gravity. It hints at the existence of something even grander, a web of cosmic construction that we are only just beginning to map. And so the universe began to build, not with a single event, but through a series of gravitational conversations. When two galaxies meet, the result is nothing like a highway pileup. The space between stars is so incomprehensibly vast that the galaxies pass through one another, a ghostly intermingling where direct stellar impacts are almost unheard of. The real violence happens in the invisible realm. Their gravitational fields, those deep wells in space-time, claw at one another. This immense, unseen force tears billions of stars from their orderly orbits, flinging them into the desolate outskirts. There they form a vast spherical cloud around the merged galaxy, a structure known as the galactic halo. This halo is not a featureless fog. Look closely, and you will see its history written in long, elegant ribbons of stars, structures astronomers call stellar streams. These are the ghostly remnants of smaller galaxies that are pulled apart and devoured. A brilliant example is unfolding right now in our own cosmic backyard. The Sagittarius dwarf spheroidal galaxy is in the slow, agonizing process of being cannibalized by the Milky Way. Its stars are being stripped away, leaving behind a luminous river that wraps around our entire galaxy. These streams are more than just beautiful relics. They are archaeological records preserving the story of past mergers. Each ribbon is a frozen snapshot of a gravitational encounter, and by tracing their paths, we can map the invisible contours of our galaxy's dark matter halo. They are the visible scars of ancient collisions, a timeline of growth written in starlight, showing us that a galaxy is not a static island, but a dynamic structure that grows and evolves by consuming its neighbors. This violent gravitational dance does more than just rearrange stars, it forges them. Within the colliding galaxies, immense clouds of gas and dust are suddenly squeezed. This cosmic compression acts like a universal trigger, igniting ferocious waves of star birth on a scale almost impossible to comprehend. Astronomers call these brilliant, chaotic events starbursts, and they are the universe's most prolific stellar nurseries. Look at the Antennae galaxies, a pair locked in a breathtaking embrace. There you can see the result, clusters of young, intensely blue stars shining like diamonds scattered across the chaos. These are not gentle births, they are a firestorm of creation, a brief, brilliant flash of new light in the cosmic dark. But this starburst is only one part of a deeper transformation. The graceful spiral arms of a galaxy, once so defined, are pulled and stretched beyond recognition. The ordered rotation is shattered, and over time, the entire structure collapses into a new form, a smooth, round, elliptical galaxy. This is a true metamorphosis, a fundamental change in identity. The galaxy loses its distinct features, becoming a vast, featureless ball of older stars, its days of active star formation largely over. This transformation is permanent, altering the galaxy's future and its role in the cosmic web. In this way, a collision is the universe's great recycler, taking the raw material of ancient gas clouds and forging it into entirely new generations of stars and solar systems. The brilliant flash of a starburst is the visible sign of this cosmic rebirth, a fleeting moment of intense creativity that leaves a completely different world in its wake. Yet within the heart of this galactic chaos, a deeper transformation is taking place. As the galaxies merge, their central supermassive black holes begin a slow, cosmic dance. These gravitational titans, each with a mass of millions or even billions of suns, are pulled from their orbits. They spiral inward, drawn toward the very center of the new galaxy they are helping to create. This is not a quick process, it unfolds over millions of years, a slow waltz set to the music of gravity. As they draw closer, they churn the surrounding space, pulling immense clouds of gas and dust along with them. This infalling material doesn't just vanish, it spirals into an incredibly hot, bright disk around each black hole. This process ignites the most luminous engines in the universe, known as active galactic nuclei or quasars. A single quasar can outshine every single star in its host galaxy combined, becoming a beacon visible across the cosmos. But this brilliance is more than just a spectacular light show, it is a force of cosmic regulation. The intense radiation and powerful jets erupting from these active hearts blast outward, heating the surrounding gas or blowing it completely out of the galaxy. This removes the very fuel required for new stars to form, effectively putting a brake on the galaxy's star-making frenzy. This feedback mechanism is a critical part of galactic evolution, a balancing act where the central black hole helps determine the galaxy's future. It can quench star formation, leaving behind a quieter, more mature galaxy. So in the grand collision, the black holes are not just passive participants, they are active architects, using their incredible power to sculpt the final form of the new galaxy and write the final chapter of its story of creation. This gravitational tug-of-war leaves behind ghostly signatures written across the sky. As two galaxies perform their cosmic dance, their immense gravitational fields stretch one another, pulling out vast, luminous streams of stars and gas. These are tidal tails, long, graceful arcs that can extend for hundreds of thousands of light years into the emptiness between galaxies. A perfect example of this celestial sculpture is the pair known as the Mice galaxies. Seen from our telescopes, they appear as two intertwined disks, each with a long, slender tail sweeping away from the other, like two dancers spinning apart while still holding hands. These structures are not permanent. They are temporary, spectacular features that last for only a few 100 million years, a fleeting moment in cosmic time. Yet in that brief window, they serve a vital purpose. These tails and the similar bridges that can form between galaxies act as cosmic conduits. They channel immense rivers of gas, dust, and even entire star clusters from one galaxy to the other, fundamentally altering the chemical makeup and future potential of both. They are the universe's way of sharing its building blocks. For astronomers, these features are more than just beautiful, they are direct evidence. The very shape and orientation of a tidal tail acts like a fingerprint, revealing the angle, speed, and direction of the original galactic encounter. By studying the motion and composition of the material within these streams, scientists can work backwards. They can reconstruct the precise dynamics of the collision, much like a forensic team analyzing the scene of an event to understand exactly what happened and when. These luminous scars are a detailed record, a story of gravitational forces written in the language of displaced stars and flowing gas. Yet the most powerful architect in this entire process remains completely invisible. The ghostly dark matter halos surrounding each galaxy contain the vast majority of their mass, a hidden gravitational skeleton. When two galaxies collide, their visible stars are torn into streams, but their dark matter does something different. This mysterious substance does not collide, slow down, or feel friction. The two halos simply pass through one another like phantoms in the night, yet gravity still binds them. They swing back and forth, eventually settling into a new, larger, and far more complex halo. This newly formed dark matter scaffold is the true foundation of the merged galaxy. It acts as an immense, unseen glue, a gravitational anchor that holds all the visible stars and gas together. Without this dark architecture, the newly formed elliptical galaxy would simply fly apart. Its presence dictates the final rotation of the stars and the placement of ancient globular clusters. Think of a magnificent cathedral. You see the stained glass and the stone walls, but what holds the entire structure aloft is the hidden framework of buttresses and beams. In a merged galaxy, the dark matter halo is that framework. It is the silent, invisible backbone upon which every single visible feature is built, a permanent reminder that what we see in the cosmos is only a fraction of what truly exists. Galaxies are social creatures rarely found in true isolation. They gather in small bands, vast cities, and immense metropolises, all bound by the same invisible threads of gravity. This is the next level of cosmic architecture, where the collisions of individual galaxies become part of a grander, collective construction project. These structures, known as galaxy groups and clusters, are themselves the products of a hierarchical assembly. Over billions of years, smaller families of galaxies have been drawn together, merging to form these colossal gatherings. Our own Milky Way resides in a modest group, but our nearest large neighbor is the Virgo cluster, a bustling metropolis containing over 1,000 galaxies. Within such a dense environment, the quiet dance of the cosmos becomes a crowded, dynamic ballet. Close encounters and collisions between galaxies are not rare events here, they are a fundamental part of life. These frequent interactions continually reshape the member galaxies, stripping away their gas, triggering starbursts, and ultimately driving their evolution on a scale far grander than they would experience alone. This collective environment is filled with a thin, superheated gas known as the intra-cluster medium. This gas is not pristine, it is enriched with heavy elements like iron and silicon, elements forged in the hearts of stars and then violently expelled during galactic collisions and close passes. This shared reservoir, this cosmic smog, is a direct result of the countless mergers that have shaped the cluster's history. It is the breath of the metropolis, a testament to the continuous recycling and building that occurs when galaxies live in a community, showing us that the universe builds not just individual islands of stars, but entire continents of them, all interconnected by a history of gravitational encounters. The final act of a galactic merger is one of utter silence. When the two supermassive black holes at the centers of these colliding cities of stars finally spiral together and become one, they do not announce their union with a flash of light. They do something far more profound. They shake the universe. This merger unleashes a blast of energy so immense it can only be expressed as a vibration in the very fabric of reality, a ripple in space-time known as a gravitational wave. These are not waves of light or sound, but literal distortions in the stage upon which the cosmos plays out, stretching and compressing the space between objects as they pass by. Einstein's theory of general relativity predicted their existence over a century ago, a testament to the power of pure thought to uncover the universe's deepest secrets. We have already begun to listen to these cosmic tremors. Ground-based observatories have detected the chirps and rumbles from the mergers of smaller, stellar mass black holes. But the grandest events, the slow, stately dance of the supermassive black holes born from galactic collisions, produce waves with wavelengths so long they are beyond the reach of Earth-bound detectors. Their frequency is too low for our current ears to hear. This is where a new era of discovery awaits. A future mission called the Laser Interferometer Space Antenna, or LISA, is being designed to float in the quiet of space. It will open a new window onto the cosmos, one tuned to the deepest registers of the universe's symphony. By listening for these low-frequency waves, we will not just observe the final moments of a black hole merger, we will experience them. We will hear the precise moment when two gravitational titans become one, a direct probe into the dynamics of the most extreme environments imaginable. This will be the ultimate test of gravity itself, allowing us to witness the final, invisible signature of the universe's greatest acts of architectural creation, written not in light but in the trembling of space-time. The stability of a solar system is a delicate arrangement, a cosmic balancing act that can be thrown into chaos by events far beyond its borders. While stars themselves may glide past one another in a galactic merger, their planetary families are not so fortunate. The primary danger comes not from direct impact but from gravitational disruption. Consider our own solar system's distant frontier, the Oort cloud. This vast spherical shell of icy bodies lies at the very edge of the Sun's gravitational influence. During a galactic collision, the subtle but persistent tug from a passing star could easily perturb the delicate orbits of these frozen worlds. A gentle nudge from gravity could send a shower of comets spiraling inward toward the warmer inner planets. Such a comet storm would dramatically alter the climate of any world in its path, a reminder that cosmic events on the grandest scales can dictate the conditions for life locally. The risk escalates with a close stellar flyby. If another star were to pass through the outer reaches of our solar system, its gravity would act like a massive hand reaching into a finely tuned machine. The harmonious orbits of planets could be severely warped. Some worlds might be flung into wildly eccentric new paths, while others could be torn from their star entirely, ejected into the cold, dark expanse of interstellar space to become rogue planets, forever wandering between the stars. This is not merely theoretical. Astronomers have already detected such free-floating planets, silent testimonies to past gravitational upheavals in our galaxy. Yet this story of disruption is also one of renewal. The same colossal clouds of gas that fuel starbursts during a merger also carry the raw ingredients for new worlds. As this fresh gas spirals into the merged galaxy, it can settle around young, newly formed stars. There, over millions of years, this material can coalesce into brand new protoplanetary disks, triggering a late wave of planet formation. Entirely new solar systems could be built from the ashes of the old, their compositions enriched by elements forged in the hearts of stars from both original galaxies. This reveals a profound connection. The architecture of a single planet, its orbit, its very existence, is inextricably linked to the grand dance of its host galaxy. The fate of worlds and the potential for life upon them is written not just in the local conditions around a star, but in the silent, gravitational conversations between entire cities of stars. Yet the grand collisions that build massive galaxies can also create ghosts. Sometimes the cosmic chaos does not forge a brilliant new giant, but instead strips a galaxy nearly bare. The result is an ultra-diffuse galaxy, a celestial phantom as wide as our own Milky Way, but containing only a tiny fraction of its stars. Imagine a city with the sprawling footprint of a metropolis, but where the streetlights are so few and far between that the entire place is shrouded in an almost permanent twilight. This is the nature of a galaxy like Dragonfly 44, a mysterious object that appears to be made almost entirely of dark matter, its visible stars little more than faint markers for an immense, invisible gravitational presence. These ghostly structures challenge our most fundamental ideas about how galaxies are built. How could something so vast hold so little light? The answer lies in the specific violence of a past encounter. A near miss with a much larger galaxy can act like a gravitational tide, pulling away the loose outer stars and, most crucially, the gas needed to form new ones. The galaxy is left frozen in time, a faint and bloated relic of a traumatic encounter. Other collisions avoid any neat classification at all, producing cosmic oddities with bizarre and irregular shapes. These are the misfits of the galactic family, structures that defy the simple categories of spiral or elliptical. Their twisted arms, lopsided disks, and chaotic star fields are not signs of a failed creation, but direct evidence of a violent past. Each peculiar form is a unique snapshot of a gravitational encounter, a frozen moment in a dance that was not quite a merger and not quite a flyby. The path of galactic evolution is not a single, straight road leading to a predictable destination. It is a winding path full of forks and detours, capable of producing an astonishing diversity of structures. This rich tapestry of forms, from the brilliant ellipticals to the faint ghosts and the twisted irregulars, shows us that the universe values creativity. Every collision, every gravitational conversation, writes its own unique story in the stars, leaving behind a legacy of architectural wonder for us to decipher. The space between galaxies is far from empty. It holds a thin, superheated gas known as the intergalactic medium, a cosmic ocean that fills the vast voids. This is where galactic collisions reveal their role as the universe's great distributors. When galaxies merge, they do not keep their riches to themselves. The immense starbursts and the furious activity around their central black holes generate titanic forces, supernova explosions more powerful than you can conceive, and the resulting galactic winds act like cosmic cannons. They blast enormous clouds of gas, now enriched with heavy elements, out of the galaxy entirely. These elements, oxygen, carbon, and iron, were forged in the nuclear furnaces of stars and scattered by their violent deaths. This process, called metal enrichment, is a fundamental act of cosmic recycling. The material that was once locked inside a star, the very stuff that makes up planets and life, is now cast adrift into the intergalactic sea. This enriched gas becomes the raw material for the future. When gravity eventually pulls this material together to form a new generation of galaxies, those systems will be born with a richer chemical heritage. They will have a head start in building rocky planets and the complex molecules that are the precursors to life. The iron in your blood and the calcium in your bones were created in a star that lived and died long before our sun was born, and a galactic collision was likely the event that set those elements free on their journey across the cosmos. This means the chemical evolution of the entire universe, the availability of the building blocks for worlds like our own, is written in the history of these violent encounters. Every large-scale merger helps to seed the cosmos with potential, ensuring that the emptiness between galaxies is, in fact, a reservoir of future creation. A galaxy's rotation is its living signature, a unique fingerprint of motion written across billions of stars, yet this orderly spin is profoundly fragile in the face of a cosmic collision. When two galaxies merge, their gravitational interaction triggers a fundamental transfer of energy, a process that scrambles the once predictable paths of countless stars. Imagine a vast spinning disk where every star follows a neat, circular orbit. Now, introduce the gravitational chaos of an incoming galaxy. This immense force acts like a massive hand stirring the cosmic pot, injecting new mass and redirecting momentum in countless random directions. The result is a complete transformation of the galaxy's internal dynamics. The stars are no longer confined to a thin, orderly disk. Their orbits are tilted, stretched, and randomized, creating a thick, three-dimensional swarm where motion is governed more by random pressure than by a unified rotation. This is the metamorphosis from a graceful spiral to a round, featureless elliptical galaxy. The change is permanent, a fundamental shift in identity that dictates the galaxy's future for the rest of its existence. This altered state has deep consequences. Without a stable, rotating disk, the remaining gas clouds find it difficult to collapse and form new stars. The galaxy's ability to rejuvenate itself is effectively shut down, leaving it a quiet collection of aging stars. This is why astronomers can look at a modern galaxy and read its history in its spin or lack thereof. A galaxy that rotates as a coherent disk has likely lived a relatively quiet life, but one where the stars move in every direction, a chaotic ballet without a central axis, carries the indelible mark of a violent past. Its rotation or its stillness is a fossil record, a lasting testament to the ancient mergers that forged its final form. Sometimes a cosmic collision is not a slow dance, but a single, perfect strike. A smaller galaxy can punch directly through the heart of a larger spiral, a bullseye impact that sends a gravitational shockwave rippling outward through the galactic disk. This wave does not destroy the galaxy. Instead, it compresses the vast clouds of gas and dust it encounters, acting like a cosmic trigger. The result is a wave of star formation so intense it illuminates the galaxy from within, a brilliant, expanding ring of newborn stars. This creates one of the universe's most spectacular and rare structures, a ring galaxy. The Cartwheel Galaxy is the quintessential example, a perfect wheel of blue-white starlight with a bright hub at its center. The ring itself is not made of stars being moved, but of stars being born, a temporary firestorm of creation tracing the path of the initial shock. These structures are fleeting on a cosmic scale, lasting only a few 100 million years before the ring disperses, but in that time they are stunningly beautiful. They offer us a clear and precise snapshot of a specific moment in a collision's timeline. The very existence of such a perfect ring demonstrates how a precise set of initial conditions, the exact angle and speed of the smaller galaxy's impact, can produce a unique and predictable architectural feature. It shows that within the apparent chaos of galactic collisions, there is an underlying physics that can sculpt a work of art, a temporary jewel in the cosmic dark that reveals the elegant rules of gravitational construction. The largest cosmic collisions are not the only way a galaxy grows. Our own Milky Way is a testament to a quieter, more persistent form of construction. It is currently consuming several smaller dwarf galaxies in a process astronomers call a minor merger. These events lack the fireworks of two giant spirals colliding, but they are no less vital. They are the steady, gentle rain of building material that accumulates over billions of years. A prime example is the Canis Major Dwarf Galaxy, a small collection of stars believed to be in the final stages of being torn apart and absorbed by our galaxy's immense gravity. As these small systems are pulled in, they contribute their stars, their gas, and their own halos of dark matter to the greater whole. This steady accretion continuously adds to the mass of the Milky Way's outer halo, that vast, spherical cloud of ancient stars that surrounds our bright galactic disk. It also delivers a precious cargo, globular clusters. These dense, spherical swarms of hundreds of thousands of stars are like cosmic artifacts, and many of the globular clusters we see orbiting the Milky Way today are thought to be the surviving cores of long-vanished dwarf galaxies. This reveals a fundamental truth about galactic evolution. A galaxy is built through both sudden, violent mergers and a slow, persistent accumulation, a dual process of dramatic events and quiet, continuous growth that shapes its final architecture. Before two supermassive black holes can complete their final union, they often become trapped in a sustained cosmic orbit, circling one another for millions of years as a binary pair. These are not simple duos. Their immense gravitational fields create a chaotic and dynamic environment, a natural laboratory for testing the most extreme physics. As they circle, they can wobble slightly, a phenomenon known as precession, which subtly tugs on the orbits of any stars or gas clouds unfortunate enough to wander nearby. This gravitational influence imprints itself on the very core of the galaxy, reshaping the architecture of its central nucleus. The complexity deepens when a third black hole, a relic from an even earlier merger, is captured by the system. This creates a volatile gravitational trio, an unstable hierarchy where the three bodies engage in a frantic dance. In the ensuing chaos, one of the black holes is often slingshotted outward, ejected from the galaxy entirely at a significant fraction of the speed of light. This event leaves a permanent scar on the galactic core and sends a lone gravitational titan on an endless journey through the void. The presence of these multiple black hole systems, whether stable binaries or the remnants of a violent ejection, serves as direct and lasting evidence of a galaxy's violent past. They are the final, enduring signatures of ancient collisions, a hidden architectural blueprint written in the silent, orbiting darkness at the heart of a galaxy. Deep within the swirling heart of every galaxy, there exists another invisible force, a subtle but pervasive presence woven through the void between the stars. These are galactic magnetic fields, vast and intricate structures that permeate the entire cosmic disk. They are thought to be generated and sustained by a dynamo effect, a process powered by the galaxy's own steady rotation, much like the dynamo on a bicycle that uses spinning motion to create light. But when two galaxies collide, this orderly spin is thrown into chaos. The very engine that powers the magnetic field is disrupted. The galaxy's rotation, once a stable foundation, is scrambled by the immense gravitational forces of the merger. This sudden, violent alteration can dismantle the established magnetic architecture, leaving the field disoriented and weakened, its cosmic blueprint erased. Yet from this disruption, a new field is born. As the colossal clouds of gas are stretched and compressed during the collision, the magnetic lines of force are pulled along with them. They are twisted, folded, and amplified within the turbulent flows, forging a new, complex magnetic web that reflects the altered state of the galaxy. This restructured field is not merely a curiosity, it actively shapes the aftermath of the collision. It influences the paths of high-energy cosmic rays, guiding these elusive particles as they travel through the galactic environment. It can also subtly regulate the final stages of star formation, as the magnetic pressure within gas clouds either helps them resist collapse or facilitates their fragmentation. While these magnetic signatures are incredibly difficult for our telescopes to detect directly, they form a fundamental part of the interstellar fabric. Their silent evolution during a merger is a crucial piece of the puzzle, revealing yet another layer of the profound metamorphosis that rebuilds a galaxy from the inside out. Our own galaxy is living on borrowed time. 4.5 billion years from now, the Milky Way and the Andromeda galaxy will begin a gravitational embrace that will last for eons. This is not a distant hypothetical. It is a future event written into the very motion of the stars we see tonight. The Andromeda galaxy, currently a faint smudge in the constellation named for the mythical princess, is hurtling toward us at a speed of over 100 kilometers every second. As the merger commences, its presence in our night sky will transform from a subtle blur into an impossible, sprawling tapestry of light. The familiar band of our own Milky Way, that river of stars arching overhead, will begin to warp and twist under the immense gravitational strain. The two spiral structures, so beautiful and distinct, will start to lose their identities, their arms pulled into long, luminous streams that wrap around one another in a cosmic dance. For any observer on a future Earth, the sky will become a spectacle of unimaginable scale, a front-row seat to the greatest architectural project our local universe will ever undertake. This slow-motion collision will fundamentally reshape our galactic home, eventually forging a new, larger elliptical galaxy that astronomers have playfully nicknamed Andromeda. What does this mean for our solar system? The sheer emptiness of space is our greatest protector. While the Sun will almost certainly be flung into a wildly different orbit within the new galaxy, the vast distances between individual stars make it incredibly unlikely that our solar system will suffer a direct impact. The planets will likely continue their orbits around the Sun, but they will do so within a completely rearranged celestial city. This impending future is the ultimate proof that we do not live in a static universe. The cosmos is a work in progress, and our own galaxy is an active construction site, its final form still being written in the silent, relentless pull of gravity. We can never watch a galaxy merger unfold in real time. Our entire civilization, from its first sparks to its distant future, is but a single, fleeting moment in a cosmic dance that lasts for billions of years. So how can we possibly hope to understand the intricate steps of this dance? The answer lies not only in our telescopes, but in the silent, mathematical power of computers. Astronomers have built entire virtual universes inside machines, vast digital laboratories where they can recreate the laws of physics and watch them play out over eons in a matter of weeks. These are not simple animations, they are sophisticated simulations like the IllustrisTNG project, which uses complex equations to model the gravitational pull of dark matter, the hydrodynamics of cosmic gas, and the fiery birth and death of stars. Within these digital realms, scientists can initiate a galactic collision and observe every consequence. They watch as invisible dark matter halos weave together, as tidal tails of stars are flung into the void, and as shockwaves compress gas to ignite starbursts. This virtual experimentation is crucial because it allows researchers to test their theories. They can run a simulation with a specific angle of impact or a certain ratio of dark matter, then compare the final, virtual galaxy to a real one observed by the Hubble or James Webb Space Telescopes. If the simulated galaxy matches the real one in its shape, its stellar streams, and its rotation, it confirms that the underlying physics in the model is likely correct. These simulations do more than just recreate what we have already seen. They predict cosmic futures we have not yet witnessed. They show us the likely fate of our own Milky Way and Andromeda, and they reveal how the faint, ghostly galaxies we are only now discovering could have been formed by past encounters. By turning the abstract mathematics of gravity and fluid dynamics into a visual, unfolding story, these computer models have become our most powerful tool for deciphering the hidden blueprints of the universe. They are the time machines that allow us to witness the grand architectural sweep of cosmic history, compressing billions of years of silent construction into a narrative we can finally see and understand. This vast cosmic tapestry, woven from filaments and voids, is the ultimate expression of the universe's hidden architecture. We must pull our perspective back, far beyond the fate of a single galaxy, to see the full picture. The universe on its grandest scale resembles a magnificent, three-dimensional spiderweb, with brilliant knots of galaxy clusters connected by long, delicate strands of galactic filaments, all surrounding unimaginably empty, dark voids. This is the cosmic web, and galactic collisions are the very engines that build it. Think of the dark matter filaments as the invisible scaffolding of the universe, the underlying framework upon which everything visible is hung. Galaxies do not form randomly in the void. They are born along these dense, river-like currents of dark matter. Gravity steadily pulls them along these preordained pathways, funneling them toward the intersections, the dense nodes where thousands of galaxies will eventually gather into massive clusters. The growth of this entire web is a direct hierarchical process. It begins with the smallest structures, the tiny proto-galaxies from the cosmic dawn, merging to form larger ones. These then collide and combine, building the luminous cities we see today. This process of assembly, of smaller pieces merging into ever larger structures, is the fundamental creative force of the cosmos. It is a chain reaction of construction that started with those minute ripples in the early universe and continues to shape the cosmos we see around us, a continuous cycle of cosmic architecture unfolding across billions of years. Within the brilliant cities of galaxy clusters, a ghostly light permeates the darkness. This is not the sharp glow of individual galaxies, but a faint, diffuse radiance that fills the immense spaces between them. Astronomers call this phenomenon intra-cluster light, and it is one of the cosmos's most elusive signatures. Its origin is a story of gravitational theft. In the crowded core of a massive cluster, galaxies swing past one another at tremendous speeds. During these close encounters, their immense gravitational fields act like tidal forces, pulling at one another's outer stars. Millions, even billions of stars can be ripped from their galactic homes in this process. But these stars are not lost to the void. Instead of flying away, they become trapped by the collective gravity of the entire cluster, a gravity dominated by its immense halo of dark matter. These orphaned stars then form a vast, thin sea of starlight, forever bound to the cluster itself rather than to any single galaxy. Observing this light is a monumental challenge, as its faint glow is often 10,000 times dimmer than the darkest sky we see from Earth. It requires long exposures with the world's most powerful telescopes to even detect it, yet the effort reveals a cosmic fossil record. The color of this diffuse light holds clues. It is typically redder than the light from many of the cluster's galaxies, indicating that the stripped stars are often older, red giants, stars that were likely in the outer halos of their original galaxies. By mapping the distribution and color of this ghostly glow, astronomers can work backwards. They can reconstruct the history of the cluster, estimating how many mergers and close encounters have occurred over billions of years and how much total mass has been stripped away from the member galaxies. This faint, pervasive light is therefore a hidden archive, a luminous history book that tells the story of the cluster's violent evolution and the countless gravitational interactions that have shaped its present architecture. This brilliant flash of a quasar is far more than a beacon, it is a cosmic regulator. When a galactic collision ignites this incredible engine, the resulting radiation and supersonic jets of particles blast outward. They drive powerful winds that sweep through the galaxy, a hurricane of energy that can push immense clouds of star-forming gas completely out into the void. Astronomers call this process active galactic nucleus feedback, a self-imposed limit on a galaxy's growth. This cycle is a fundamental act of cosmic regulation. The very same event that triggers a firestorm of star birth also carries the mechanism to end it. By expelling its own gaseous fuel, the galaxy effectively quenches its ability to create new stars. Over time, this transforms the galaxy's character. A once blue and vibrant spiral, rich with young, hot stars, slowly turns red and quiet, its stellar population aging without renewal. This feedback loop explains a profound pattern we see across the universe, the clear division of galaxies into two distinct families. On one side are the blue, star-forming spirals, and on the other are the red, quiescent ellipticals. The collision does not just build a galaxy, it also writes its final chapter. This self-regulating cycle ensures that galaxies do not grow without bound, imposing a natural limit on their size and luminosity. The violent chaos of a merger, therefore, contains its own balancing force, a built-in mechanism that helps sculpt the mature and orderly universe we observe today. The stability required for life is a fragile thing, even on a galactic scale. For a world to nurture complex organisms, its location within its home galaxy matters profoundly. Astronomers call this the galactic habitable zone, a theoretical band where conditions are just right. It must be far enough from the crowded, radiation-blasted core to avoid deadly cosmic rays and frequent supernova, yet close enough to have sufficient heavy elements to form rocky planets. It is a delicate balancing act, a celestial sweet spot. A major galactic collision shatters this stability. The sudden, violent burst of star formation floods entire spiral arms with intense radiation, effectively sterilizing regions that were once calm. A planetary system orbiting peacefully in a quiet suburb could find its neighborhood transformed into a chaotic downtown, its atmosphere bombarded by energy from newborn stellar giants. The gravitational reshuffling itself poses a silent threat. A star and its planets, once safely distant from any known supernova remnants, could be flung onto a new path that takes them directly through the lingering aftermath of an ancient stellar explosion. The habitable zone is not a permanent address but a temporary state of grace. Yet within this chaos lies a counterpoint of creation. The same collision that disrupts one region can sow the seeds for another. Vast inflows of fresh gas can settle in the galaxy's outer reaches, far from the dangerous core. In these new, quiet suburbs, the process of planet formation can begin anew, creating pristine solar systems with all the necessary ingredients for life, but in a much calmer environment. The architecture of habitability is therefore a dynamic blueprint, constantly being redrawn by the gravitational encounters that reshape the galaxy itself. A world's potential for life is not just about its star, but about the silent, historical dance of its entire galactic home. The chaos of a galactic collision can fling stars across the cosmos like stones from a sling. While most stars are simply rearranged within the newly merged galaxy, a select few receive an incredible burst of speed, becoming hypervelocity runaways. These are stars ejected from their home galaxy entirely, now traveling at speeds so immense they can escape the galaxy's gravitational pull forever. Their journey begins in the most chaotic region of all, the very heart of the merging system where the supermassive black holes perform their gravitational dance. As these black holes spiral inward, their complex interplay creates a volatile environment. A star that ventures too close can be caught in their gravitational field, whipped around one black hole, and then flung outward by the other in a precise slingshot maneuver. The star is launched on a one-way trip into the vast, empty darkness between galaxies. These hypervelocity stars are more than just celestial curiosities. They are forensic evidence. Each one carries a unique signature in its speed and composition, a coded message about the violent event that created it. By carefully measuring a runaway star's trajectory and velocity, astronomers can perform a kind of cosmic backtracking. They can rewind its path across millions of light years, tracing its origin back to a specific galaxy or even a specific cluster of galaxies that underwent a merger in the distant past. This turns these lonely travelers into probes, helping us map the history of violent encounters throughout our cosmic neighborhood. They are the shrapnel from a galactic construction site, and by studying their flight, we can locate where the universe's most monumental building projects have taken place. The largest cosmic structures did not appear fully formed. They were assembled piece by piece from the smallest units of matter the early universe could provide. The first true galaxies to ignite were not the majestic spirals we know today, but vast populations of tiny, faint dwarfs. These were the universe's original bricks, the fundamental building blocks in a hierarchical construction project of staggering scale. In this model, gravity works from the bottom up. Small dwarf galaxies, rich with the first stars, were drawn together by their mutual attraction. They merged 2 or 3 at a time, forming slightly larger structures. These, in turn, collided and combined, slowly building up the mass and complexity that would eventually define a giant spiral or a massive elliptical galaxy. The evidence for this process is written in the faint halo of our own Milky Way. This vast spherical cloud of ancient stars is not a uniform fog. It is an archaeological dig site, its layers composed of the ghostly remnants of countless dwarf galaxies consumed over billions of years. When we look at a present-day dwarf galaxy like the Large Magellanic Cloud orbiting our own, we are looking at a pristine example of those initial bricks. These small systems are living fossils, preserving the conditions and the elemental makeup of the universe's first galactic structures. By studying them and the stellar streams they leave behind as they are torn apart, we are reading the original blueprints. We see the initial conditions from which all larger-scale architecture emerged, the simple, fundamental units that gravity used to assemble the entire cosmic cathedral we observe today. The universe has given us a unique gallery, a collection of snapshots that together form a complete timeline of cosmic construction. Instead of waiting billions of years to watch a single merger, we can simply look out into the cosmos and find galaxies frozen in every stage of this grand process. It is a living flipbook of galactic evolution, with each page telling a different part of the same story. The first chapter begins with a gentle, gravitational introduction. Look at the Whirlpool Galaxy, a stunning spiral with a smaller companion galaxy held in its sway. They are still widely separated, but the smaller galaxy's gravity is already starting to distort the Whirlpool's perfect spiral arms, pulling one of them into a visible curve. This is the opening act, where two independent systems first begin to feel each other's presence, their futures now irrevocably linked. Then we turn the page to the middle of the story, to systems like the antennae galaxies. Here, the collision is in full, violent swing. The two galactic cores are clearly visible, but their spiral structures are gone, shredded into those spectacular, long tidal tails that give the pair its name. The space between them is ablaze with the pink glow of stellar nurseries, a ferocious starburst triggered by the immense compression of gas clouds. This is the chaotic climax of the narrative. Finally, we see the last page, the aftermath. Many of the smooth, round elliptical galaxies we observe are the quiet endpoints of this violent drama. They bear the hallmarks of a finished merger, their stars orbiting in every direction, their gas supplies depleted, their days of frantic star formation long over. They are the serene-looking end results, the completed architectural projects. This cosmic gallery is more than just a beautiful collection. It is a vital scientific tool. By arranging these different observed stages into a sequence, astronomers can construct a detailed timeline of galactic evolution. They can directly test the predictions of their complex computer simulations, checking if the virtual galaxies they create match the real ones we see at each step. Does a simulated collision produce tidal tails like the antennae? Does it ultimately form a galaxy that looks like the quiet ellipticals in our surveys? This continuous cross-check between observation and simulation is how we refine our understanding of the universe's hidden blueprints, confirming that the forces we believe are at work are truly sculpting the cosmos we see. These dense, spherical swarms of ancient stars hold secrets that reach far back into cosmic time. Orbiting in the vast halo of a galaxy, globular clusters are like celestial artifacts, each one a compact city of hundreds of thousands of stars, all born together in the distant past. When two galaxies collide, their populations of these ancient clusters are thrown into a profound rearrangement. A larger galaxy does not merely consume the stars of a smaller companion. It captures its entire system of globular clusters, pulling them into new, often chaotic orbits. This process can dramatically enrich the halo of the dominant galaxy, leaving it with a vast and varied collection of these stellar fossils. But the story does not end with capture. The violent compression of gas during the merger can itself become a crucible for new cluster formation. Within the immense shockwaves that ripple through colliding gas clouds, conditions can become so dense and pressurized that they trigger the birth of entirely new globular clusters, right in the heart of the chaos. This means a single merger can leave behind two distinct kinds of evidence: clusters it stole and clusters it forged. Because of this, the entire system of globular clusters orbiting a galaxy becomes a unique historical archive. An elliptical galaxy with a surprisingly large number of clusters, or with populations that have clearly different ages and chemical compositions, is telling a story of a violent past. It is showing us the ghostly signatures of smaller galaxies it consumed long ago. This independent line of evidence perfectly corroborates the tale told by stellar streams and tidal tails, building a consistent and compelling picture of a galaxy's growth through relentless gravitational encounters. The quiet, round shape of an elliptical galaxy is often the final signature of a cosmic merger, but how can we be certain? The evidence is not always obvious, written in faint stellar echoes that require a careful eye to decipher. Look beyond the galaxy's bright core and you might see them ghostly shell structures. These are faint, concentric arcs of stars, layered around the galaxy like the rings inside a tree trunk. Each shell is a frozen ripple, a relic of a gravitational shockwave from a smaller galaxy being torn apart and consumed. They are the aftermath of a splash in a galactic pond, marking the rhythmic settling of stars after a violent union. This is forensic astronomy at its finest, reading the subtle scars left by ancient events. Another clue lies in the galaxy's internal motion. Sometimes, astronomers observe a disk of cold gas at a galaxy's center that is tilted at a strange angle, or even rotates in the opposite direction to the vast majority of the galaxy's stars. This misalignment is a profound anomaly. It tells a story of new material arriving from an unexpected direction, a gift from a devoured companion that never fully mixed with the established population. These are not gentle additions, but violent insertions that leave a permanent, dynamical scar. By collecting these clues, the shells, the misaligned disks, the counter-rotating stars, astronomers become cosmic historians. They can classify galaxies not just by how they look today, but by the dramatic events that forged them. Each piece of evidence is a paragraph in a much longer story, allowing us to reconstruct the narrative of how our present-day universe, with all its magnificent variety, was assembled from countless smaller pieces over billions of years of relentless gravitational construction. Gravity has spent billions of years building the cosmic web, but another, more mysterious force is working to unravel it. This is dark energy, a phenomenon that causes the expansion of the universe to accelerate, not slow down. For most of cosmic history, gravity was the dominant architect, tirelessly pulling galaxies together to construct the magnificent filaments and clusters of the cosmic web. Now, a great cosmic tug-of-war is underway. Dark energy acts as a counterforce to gravity's relentless pull, creating a fundamental tension that will decide the ultimate fate of everything we see. As the expansion accelerates, the vast voids between galaxy clusters grow ever wider and emptier. The distances that gravity must bridge to pull galaxies together become insurmountably large. In the far future, this accelerating expansion will bring the era of galactic construction to a permanent end. No new mergers will occur, and the cosmic web will stop growing. The great architectural project of the universe will cease, frozen in time as the threads of the web are stretched and isolated. This means we are living in a uniquely privileged moment, a cosmic golden age. We exist in the narrow window of time after gravity has built these colossal structures, but before dark energy has pushed them forever out of reach. We can still witness the vibrant, dynamic collisions that build galaxies and weave the cosmic tapestry. Future civilizations, if they arise in a universe dominated by dark energy, would gaze out into a much darker and lonelier cosmos, where other galaxies have faded from view and the evidence of this grand construction is lost. Our ability to see this cosmic architecture is a fleeting gift, a special chapter in the story of the universe where its hidden blueprints are still visible to us. A galactic collision is a symphony of light, but our eyes are deaf to most of its music. We see only a single note, the visible starlight that outlines the dance of giants. To truly hear the entire composition, we must listen across the entire electromagnetic spectrum, from the deep bass hum of radio waves to the piercing, high-energy shriek of X-rays. Each wavelength reveals a different instrument in this cosmic orchestra. Optical telescopes show us the stars themselves, the bright, visible players on the stage. But look through an infrared eye like that of the James Webb Space Telescope, and you peer straight through the obscuring curtains of dust and gas to witness the hidden firestorms of star birth blazing within. Meanwhile, radio telescopes such as the VLA map the vast, cold reservoirs of hydrogen gas, the unseen river flowing between the galaxies, and detect the faint synchrotron radiation that traces the presence of powerful magnetic fields and cosmic rays accelerated in the chaos. Then, shifting to the highest energies, X-ray telescopes like Chandra pinpoint the superheated, million-degree gas shocked by the collision, and illuminate the furious, glowing disks of material spiraling into the supermassive black holes at the galaxy's hearts. Each of these views is a crucial piece of the puzzle. One stunning example is the mapping of immense hydrogen gas bridges between interacting galaxies, structures completely invisible in optical light, yet fundamental to understanding how raw material is transferred during a merger. Without this multi-messenger approach, we would be like someone trying to understand a complex machine by looking at only one of its gears. We would see motion, but we would never comprehend the engine. The faint glow of the cosmic microwave background is the oldest light in the universe, a baby picture taken when the cosmos was just 380,000 years old. This radiation bath is not perfectly smooth. It holds tiny, almost imperceptible variations in temperature. These minute fluctuations are the universe's original blueprints, the gravitational seeds from which every galaxy, cluster, and filament would one day sprout. The grand collisions that build galaxies today do not reach back to touch this ancient light directly. Instead, their immense legacy, the colossal structures they help assemble, leaves a final, subtle signature upon it. When light from this primordial glow travels across the cosmos on its journey to our telescopes, it must pass through the modern universe's great cities, the massive galaxy clusters. Within these clusters, the space between galaxies is filled with a searingly hot gas. As the ancient CMB photons pass through, they occasionally collide with the energetic electrons in this gas. This interaction gives the photons a slight boost of energy, a subtle change that astronomers can detect. This phenomenon, known as the Sunyaev-Zeldovich effect, creates a specific kind of shadow in the microwave sky, a cold spot against the warmer background. It is not an absence of light, but a distortion, a fingerprint left by the cluster's hot electrons on the most ancient radiation we can see. This provides a powerful, independent way to map the universe's hidden architecture. By surveying the sky for these distortions, we can locate the most massive galaxy clusters, even those that are otherwise too faint to see, because the effect depends not on the cluster's visible light, but on the sheer density of its hot gas. This method reveals the gravitational weight of these cosmic metropolises, allowing us to trace the distribution of all mass, both visible and dark, across the vast expanse of space. The silent construction of the cosmic web, powered by eons of collisions, thus inscribes its final mark upon the universe's very first light. Every collision tells a different story because no two galaxies meet under the exact same circumstances. The final architecture of a merged galaxy is not written in stone, but is instead shaped by a delicate interplay of initial conditions. Consider the simple act of approach. A direct head-on impact where two galactic cores are aimed directly at one another will produce a massive, round elliptical galaxy almost immediately. But a gentle, glancing blow is an entirely different kind of event. In that scenario, the galaxies might swing past each other, their gravitational pull stretching them into long, graceful tidal tails before they eventually fall back together in a slower, more drawn-out dance. The relative speed matters too. A high-speed encounter is like a brief, disruptive pass, often leaving both galaxies wounded but still distinct. A slow, ponderous merger allows for a more complete and thorough mixing, a true blending of two systems into one entirely new entity. Even the internal composition of the galaxies introduces another variable. A gas-rich spiral colliding with another gas-rich spiral will ignite a brilliant, fiery starburst, while two gas-poor ellipticals merging will simply create a larger, redder, and quieter elliptical with little fanfare. This inherent randomness is the reason we see such a stunning variety of forms in the night sky. The universe is not operating from a single, rigid blueprint. It is more like a vast, dynamic workshop where gravity is the master builder, but chance supplies the materials and the specific instructions for each unique project. This stochastic element means that the cosmic architecture we observe is not the product of a predictable assembly line, but the beautiful and unexpected result of countless unique gravitational conversations. This serene night sky above us is a beautiful deception, a fleeting moment frozen in a story of relentless change. Those points of light we see as permanent fixtures are actually cities of stars engaged in a slow, gravitational dance that spans billions of years. Our own galaxy, the Milky Way, is not a finished monument but a work in progress, its current form merely one chapter in a much longer biography of collisions and mergers. This realization does more than just update a scientific fact. It fundamentally alters our relationship with the cosmos. We are not simply looking at a static picture, we are living inside an evolving system, one where the very structures we consider permanent are temporary waypoints in an endless cycle of construction. What does it mean for our sense of place to know that the celestial ground beneath our feet is moving, that the galactic neighborhood we call home is destined to merge with another, creating an entirely new world of stars? This perspective invites a profound philosophical shift. We are asked to accept impermanence on the grandest possible scale. If a galaxy, an entity of hundreds of billions of stars, is not an eternal island but a temporary structure in a continuous flow of growth and transformation, then change is not an exception to the cosmic order, it is the cosmic order. The universe appears to be less like a finished cathedral and more like a living, breathing entity, constantly building and rebuilding itself. This dynamic nature challenges our deepest intuitions about stability and permanence, suggesting that existence itself may be a process rather than a state, a continuous becoming written into the hidden architecture of everything. The silent, mathematical universe we simulate on our computers is about to meet its ultimate test. A new generation of eyes is turning toward the sky, instruments so powerful they will transform our theoretical blueprints into observed, undeniable fact. The James Webb Space Telescope, with its infrared gaze, is already looking back in time, not just to see the first galaxies, but to witness their infancy, to catch them in the very act of their earliest mergers. It peers through the cosmic dust that once hid these formative collisions from view, revealing the initial chaotic steps in the assembly of the cosmic web. Meanwhile, the future Nancy Grace Roman Space Telescope will take a different approach. It will conduct vast, sweeping surveys of the sky, gathering statistics on millions of galaxies. This big data perspective will let us move beyond individual case studies to understand the rules of galactic interaction on a universal scale. We will see not just one beautiful merger, but thousands, allowing us to classify them, to understand which types of encounters are common and which are rare cosmic flukes. On the ground, the colossal eye of the extremely large telescope will bring the nearby universe into a focus we have never before experienced. It will resolve individual stars within colliding galaxies millions of light years away, tracing the intricate flows of material in tidal tails with breathtaking clarity. Together, this fleet of observatories will act as a truth machine for our simulations. Does the virtual dark matter halo formed in a computer model match the gravitational lensing effects we can now precisely measure? Do the predicted rates of star formation in a simulated starburst align with the chemical signatures we detect in real galaxies? Each observation is a data point that either confirms our understanding or forces a thrilling revision. This is not the end of discovery, but a new beginning. With such powerful tools, we are almost certain to find new classes of galactic interactions, phenomena that our current models have not yet dreamed of. We will refine the hidden architecture of the universe, not by redrawing the blueprints from scratch, but by filling in details we never knew were missing, revealing a cosmos more complex and more beautifully constructed than we ever imagined. Even with our most powerful tools, the blueprint of the cosmos is still filled with question marks. We can map the stunning consequences of galactic collisions, but the precise mechanics of their construction remain shrouded in mystery. One of the most profound puzzles centers on dark matter. We know its immense gravitational pull orchestrates the entire merger, weaving the halos that become the final galaxy skeleton. But what is this substance? How does it interact with itself and with the ordinary matter we see? Our simulations rely on certain assumptions about its behavior, but we have no direct proof, leaving a ghostly uncertainty at the very heart of the architectural process. Then there is the enigmatic final dance of supermassive black holes. We understand they spiral together, but the final steps are maddeningly unclear. How do they shed enough energy to close that last tiny gap and finally become one? Does a final nudge from surrounding stars and gas complete the merger, or are there other, more exotic physics at play that we have not yet conceived? The answers are locked within the low-frequency gravitational waves we cannot yet hear, a silent hum of information just beyond our current reach, and what of the universe's own regulatory systems? The feedback from brilliant quasars and furious starbursts clearly shapes a galaxy's growth, but the detailed physics of these cosmic hurricanes is incredibly complex. How exactly does energy from the center communicate with the outer gas clouds to either trigger or quench star formation? The balance is delicate, and we are still learning the rules of this cosmic conversation. Perhaps the most visually striking mystery is why the universe chooses one final form over another. Why does one collision produce a smooth, round elliptical galaxy, while another, against all odds, seems to regather its gas and reform a beautiful spinning disk? The initial conditions of the merger, the amount of gas, the angle of impact, all must play a part, but the exact recipe for a spiral galaxy's rebirth remains an unsolved equation. This vibrant field of research is a testament to our endless curiosity. Every time we answer one question, it peels back to reveal another, deeper layer of the puzzle. The hidden architecture of the universe is a complex code, and we are only just beginning to crack the first few symbols, driven by a fundamental need to understand where we came from and what our cosmic home will ultimately become. From the gentle reign of dwarf galaxies to the spectacular merger of giants, We have traced the work of the universe's master architects. These collisions build the galaxies we see, trigger the fiery birth of stars, fuel the brilliant hearts of black holes, and weave the immense cosmic web that structures everything. For billions of years, gravity has been the silent sculptor of this hidden architecture, revealing a cosmos that is profoundly dynamic and ever-changing. The tranquil night sky is a beautiful illusion, a snapshot of a construction project that never ceases. When you next gaze upward, remember the slow-motion ballet unfolding in the darkness, a dance of creation that built the very ground of stars beneath our feet. If this journey through the cosmos has reshaped your view of the universe, consider subscribing for more explorations into its deepest mysteries. We would love to hear your thoughts on these celestial collisions in the comments below.